So far we have considered the phenomena where if a sample space is given, we are considering function of a the function which is the mapping sample space to the real line. So, we are considering one characteristic at a time. For example, it may be heights of the students, it may be marks of students in a test paper, it may be the life of an electronic equipment. However, so this constitutes the values of a single random variable x. So, we have so far concentrated on the distribution of the random variable x. Many times we are not having the luxury of considering only one characteristic, but several characteristics, such as a patient goes to a doctor for a medical checkup. The doctor takes his say temperature, he may take his blood pressure, he may take his pulse rate, and he may record his say weight. So, for different patients 4 quantities x 1, x 2, x 3, x 4 are recorded. So, here this constitutes a random vector or jointly distributed random variable x 1, x 2, x 3, x 4. So, x is called a random vector. We may be looking at say x 1 as marks in paper 1, x 2 as marks in paper 2, say x 5 marks in paper 5. So, students are studying 5 subjects in a particular semester, and each of them will get different marks in different test papers. So, for each student, if we record x is equal to x 1, x 2, x 3, x 4 and x 5, then this is a random vector or a jointly distributed random variables x 1, x 2, x 3, x 4 and x 5. So, in general, if I am considering x as x 1, x 2, x k, then this is a function from omega into the k dimensional Euclidean space R k. The random variable x was a measurable function from omega into R, that is one dimensional Euclidean space. So, a higher order random variable or a random vector is a function from, it is a measurable function from omega into R k. So, x is measurable function that we have to ensure in order that the probability functions of x are well defined. For convenience, we will restrict attention to 2 dimensional case in the beginning. So, let us consider jointly distributed random variables x y. So, here x could denote the height of a newborn and y could denote the weight of a newborn baby. X y could denote the coordinates of a dart hitting a target. So, suppose this is the target, we consider it as origin and the dart may hit anywhere. So, the coordinates x y of the dart hitting may be considered as a jointly distributed random variable. Suppose we are considering crop in a area. So, crop in a say Rabi season and in a Kharif season in a year. We may consider say export growth say x and say import growth y in a quarter of a year for a country. So, these are all examples of jointly distributed random variables. Now, naturally the question arises that how do we evaluate the probability distribution of x y, or how do we define the probability distribution of jointly distributed random variables. So, we have seen in the case of one variable, the description of the probability distribution depends upon whether the random variable is discrete or continuous. So, if the random variable is discrete, we have a probability mass function. If the random variable is continuous, we have a probability density function. Of course, for any type of random variable, we have the facility of using a cumulative distribution function, but that is not useful all the time. So, when we have a jointly distributed random variable, then there can be several cases. X may be discrete, y may be continuous, both may be discrete, both may be continuous, x may be discrete, y may be a mixture, x may be a mixture random variable, y may be continuous, etc. So, in each case the description of the distribution may be of different nature. However, one may make use of the joint CDF, that is probability of x less than or equal to x, y less than or equal to y. This is defined for all x y in the two dimensional plane. So, we will look at the properties of this CDF later on. Firstly, let us consider the case when both x y may be discrete or both x y may be continuous. So, if both x and y are say discrete, that means the values that x y take in a space say x cross y, this is finite or at most countable. So, in this case the probability mass function of x y, this will satisfy. So, p x probability x equal to x, y is equal to y. Let me put here x equal to x I, y is equal to y j, because the values are at most countable. So, we can enumerate them. This is p x y x I y j for all x y x I y j. Then this function is always non-negative for all x I y j, and the sum over all the values of the probability mass function is 1. Let us take one example here. Suppose a car showroom has 10 cars of a brand, out of which 5 are good, 2 are having say defective transmission, and 3 have say defective say steerings. So, we call it say DT and DS, and good are G. Now, if 2 cars are selected at random, let x denote the number of cars with defective transmission and y the number of cars with defective steering mechanism. So, here x y is a discrete random vector, both x and y can take values 0, 1, 2. So, the probability distribution of x y can be described what is the probability that x is equal to 0, y is equal to 0. Now, this is possible if both of the selections are made from the good 5 cars out of the total selections from 10. So, this is equal to 10 by 45 or 2 by 9. Similarly, we can calculate probability x is equal to 0 and y is equal to 1. So, here it means that out of 5 good, 1 good car has been selected, and out of 3 cars with defective steering mechanism, 1 has been selected out of total 2 selections of 10. So, that is equal to 15 by 45 or 1 by 3. In a similar way, we can calculate all other probabilities, and we can describe the probability distribution in the form of a tabular representation. The probability x equal to 0, y is equal to 0 is 10 by 45. The probability x equal to 0, y is equal to 1 is 15 by 45. The probability that x equal to 0, y is equal to 2, that can be calculated to be 3 by 45. The probability that x equal to 1, y is equal to 0 can be calculated to be 10 by 45. X is equal to 1, y is equal to 1, 6 by 45. X is equal to 1, y is equal to 2 is not possible, because total selections are only 2. So, this is 0. Probability that x equal to 0, y is equal to 2, y is equal to 0 is 1 by 45. Again 2 1 and 2 2 are not possible. So, this gives the joint distribution p x y of the random variables x y. You can look at various probabilities related to random variables x y from here. For example, if we ask the question, what is the probability that x is say less than or equal to 1, y is less than or equal to 1. Then this is corresponding to probability of x is equal to 0, y is equal to 0, probability x is equal to 0, y is equal to 1, probability x equal to 1, y is equal to 0, and probability x equal to 1, y is equal to 1. So, this is equal to 10 by 45 plus 15 by 45 plus 10 by 45 plus 6 by 45, which is equal to 41 by 45. We may answer some other questions from here regarding the probabilities. For example, if we ask what is the probability x is say less than 2, that is probability x equal to 0 plus probability x equal to 1. Now, this relates to the probabilities of one random variable when the joint distribution is given. Now, notice here that if I sum row wise, then this will give probability x equal to 0, y is equal to 0, probability x equal to 0, y is equal to 1, probability x equal to 0, y is equal to 2. That means, this will give the distribution of x, that is equal to 28 by 45, 16 by 45 and 1 by 45. Similarly, if I add the columns here, I will get the distribution of y. So, that is 21 by 45, 21 by 45 and 3 by 45. So, now probability x equal to 0 and probability x equal to 1 can be easily obtained as 28 by 45 plus 16 by 45, that is equal to 44 by 45. This process of adding row wise or column wise, this gives rise to the individual distributions of x and y. They are known as marginal distributions. So, in general, the marginal distribution of x is defined as, this is obtained by adding the values of y over the range of this. Similarly, the marginal distribution of y is obtained by adding the joint probability mass function with respect to x I. So, we can answer all the probability statements regarding individual distributions of x and y also from the joint probability mass function. Now, there is one more thing, when we have two random variables, we may also look at the conditioning events. For example, if y is equal to 2 is given, if y is equal to 1 is given, what happens to the probability distribution of x? This is known as the conditional distribution. So, we may define the conditional probability mass function of x given a value, say y is equal to y j. So, this is given by the joint distribution of x and y at x I y j divided by the marginal of this, where x I varies over x. To see that it is a valid probability distribution, let us sum over all the values of x I. So, if we sum over all the values of x I, the numerator becomes the marginal distribution of y j, which is the denominator. So, this will become 1. So, this is well defined. Similarly, the conditional probability mass function of y given x is equal to x I. So, that is equal to p y given x equal to x I is at the value y j, it is defined to be the joint distribution divided by the marginal distribution of x I for values of y j over y. Once again you can see that it is a valid probability distribution. If we sum over the values of y j, the numerator here will become p x x I, which is same as the denominator. So, it will give the value 1. So, in this given problem, let us look at the conditional distribution, say probability of y given x is equal to 0. So, the values of y are 0, 1 and 2. What is the probability that y is equal to 0 given x equal to 0? So, it is p 0 0 divided by p x 0. Now, p 0 0 is 10 by 45 and p x 0 is 28 by 45. So, this becomes 10 by 28. What is p y 1 given x equal to 0? This is p 0 1 divided by p x 0. So, that is equal to 15 by 28. Similarly, p y x equal to 0 at 2, this is p 0 2 divided by p x 0, that is 3 by 28. So, you can see here the sum of the 3 probabilities 10 by 28, 15 by 28 and 3 by 28 gives 1. In a similar way, one may calculate probability distribution of say y given x equal to 1, probability distribution of y given x equal to 2. Notice here that if I say x is equal to 2, then only y is equal to 0 is possible. So, probability of y is equal to 2 given x equal to 2, that will be 1. This is a degenerate distribution. This is p 2 2 divided by probability x equal to 2, that is 1 by 45 divided by 1 by 45. Because if x equal to 2 is fixed, then y cannot take any other value except 0. Sorry, this is not 2, this is 0. Because the total number of cars that we are purchasing is 2. Therefore, if one of them is having the value 2, then the other value has to be 0. Now, in a if both the random variables are continuous, then we have joint probability density function. So, let us consider, let x and y be both continuous. So, the joint probability density function of x y is f x y. This is satisfying that it has to be a non-negative function. The integral over the whole range with respect to both the random variables is 1. So, here in place of dx dy one may write dy dx also, and if B is a measurable subset of R 2, then probability of x y belonging to B will be given by the integral of the density over the set B. Integration may be in any order. If the probability density function is given, we may be able to answer any probability statement related to the distribution of x y, the joint distribution or marginal distributions of x and y. Thank you.